let's proceed with the second important concept in the study of rotational dynamics, known as angular velocity. By definition, angular velocity is simply the rate of change of angular displacement. Angular displacement, that's all, please. So the rate of change of angular displacement is referred to as angular velocity. Full stop, please. It is represented by a Greek symbol. It's represented by a Greek symbol called omega. A Greek symbol called omega. All right. Angular velocity is represented by a Greek symbol called omega. So have omega. This symbol is omega. Mathematically, omega, this one here, is equal to, we said angular velocity, which is omega, is the rate of change of angular displacement. When it comes to rate of change, only the word rate of change is a time-bound word. So if I'm saying GANYU rate of change, it means GANYU over time. If I say calculator rate of change, it means calculator over time. And I'm saying is that angular velocity is the rate of change of angular displacement. That becomes what the angular displacement over time. That's angular displacement. That's theta over time. Please, angular displacement is theta, as we said initially from our previous concept of this. So we said this becomes the mathematical expression for angular velocity. By the way, omega signifies the angular velocity, while the theta there signifies the angular displacement, all right, and the t there signifies the time, of course, in seconds. All right, angular displacement, of course, in rad, of course, in rad. Angular velocity, okay, what's the S sign for angular velocity? Let's get S sign, please. From here we said omega is equal to what? Theta over t. So I'm saying this like theta is measured in rad. That becomes rad. All over time is in seconds. So I'm saying that the SI unit for angular velocity, so the SI unit for angular velocity is given as rad per second. Rad per second. All right. Or you use rad per second, so minus 1. So it becomes the SI unit for angular velocity. So bear in mind that angular velocity is simply the ratio of what? Angular displacement all over time, and it's measured in what? Rad per second. This becomes the concept behind angular displacement. Two things to note before we move to angular acceleration. Two things to note, please. Note number one, under this, please. Two things to note. Note number one. The relationship between angular displacement and linear velocity. Relationship between angular displacement angular velocity, please. The relationship between angular velocity, I'm under this, please, velocity and linear velocity is given by angular velocity omega is equal to v over r. Please listen and listen. I'm having angular velocity. I'm having linear velocity. Linear velocity is what you know, your v. That's your normal linear velocity. So what's the relationship between your angular velocity and the linear one? So note that angular velocity is equal to what there? The linear velocity all over what? All over r. Where the v signifies the velocity, right? Signifies the linear velocity. Linear velocity, right? That's your v. Your r signifies the radius of curvature or radius of circular paths. All right, so that's like the concept. What your this one here, omega, this one here signifies omega. So bear in mind that outside angular velocity, we know that we have normal velocity. So I'm relating normal velocity that we have and the angular one. This expression becomes the formula that relates the angular velocity and linear velocity. So this becomes the formula that relates the two of them. Please, this note number one, please. Note number two, please. This one is meter per second. Meter per second. Yes, your linear velocity. Your normal velocity is meter per second. All right, number two, please. Note number two. Note number two, please. Note number two, please. Note that one revolution is equal to 2 pi rad. Please note that one revolution is equal to 2 pi rad. So I have this way. Let me explain something, please. If I say one revolution, what does it mean? One revolution there signifies or it means when a body moves in a complete oscillation. Let's say I have my center here and a body moves this way from this point here down and go back to its original state in the circular path this way. This one here, it has complete what the one revolution. So a one revolution, a one complete full circle is equal to what? 2 pi rad. So I'm saying this, please. For you to complete one oscillation, it's equivalent to what? A 2 pi rad. Please bear in mind. Now here's the concept, please. Here's the concept. When it comes to your mensuration concept and idea in mathematics, your pi is not 20/7. Pi is what? 180 degrees. Go to calculus and other mathematics like mensuration and other concept there. You observe that theta at that level is no longer 180. Look at trig functions. Study trig function in depthly. Theta there is not 20/7. So it's 180. So I'm taking theta as 180 because I'm dealing with what? Circles and etc. So if theta pi is 180 degrees, so it means that of course what we know is that sum of angle in a circle is equal to what? 360 degrees. So one revolution means 360 degrees. This equal to 2 pi is 180. That's 180. So 2 times 180 is what? Say 360. So I'm saying that one revolution is equal to what there? 2 pi rad. They are the same thing, please. They are the same thing, please. Please, they are the same thing, please. So I don't understand this concept. Please, with this concept in service, please. So one revolution is equal to 2 pi rad. So I have this one here. So now here's the concept, please. Let's try some problem. If I have one revolution, that's 2 pi rad, Abby. if I have 1 pi rad, 1 pi rad, this one signifies what? 180 degrees. Yeah. Abi? Yeah. If I have 2 pi rad, signifies what there? 360 degrees. All right. So this is like the concept behind the second thing to note when it comes to angular velocity. Let's look at the last part called the angular acceleration and we'll proceed. Let's discuss angular acceleration and we'll proceed, please. Let's look at the last part called the angular acceleration, and then we'll look at its mathematical representation and its SI units, proceeding to solving past questions for the last 10 years under the study of rotational dynamics, please. Let's look at yet the second concept called angular acceleration. By definition, angular acceleration is simply the ratio of angular velocity is the rate of change of angular velocity. So I'm saying that angular acceleration is the rate of change of angular velocity. So stop, please. It's represented by a Greek symbol called alpha. It's represented by a Greek symbol called alpha. So I have this one here, alpha. Mathematically, angular acceleration, that's alpha, we said is the rate of change of angular velocity. That's omega all over t. That's all. Omega all over t. That's all. Omega, please. Let's define term, please. Define term where this one here, omega, signifies the angular velocity. So angular velocity, of course, rad per seconds is the SI unit. So rad per seconds is the SI unit for this, please. Rad per seconds is the SI unit. T is the time in seconds. All right, time in seconds. Why alpha there signifies the angular acceleration. So angular acceleration. All right, I have this here. Let's get a sign, please. So angular acceleration alpha is equal to angular velocity, that's omega all over t. Omega is measured in rad per second. So I have rad per seconds. This one here is for omega. All over t is in seconds. I have this, place. Break this down. The SI unit for angular acceleration now will be equal to this one here gives rad per seconds divided by this line here is this by seconds. Of course, an invisible one should be here. From here, I will have rad per second, rad per seconds. This one to times. This one comes up here, the S comes down here. Multiply through R times 1 is RAD times 1, that's rad, all over S times X gives X squared. So I'm saying that the SI unit for angular acceleration is what? It's given by rad per second squared. So rad per second square is simply the SI unit for angular acceleration as shown below. All right, I have its mathematical expression as shown in the board below here. By the way, when I gave you the concept behind angular velocity, I said note two things. When it comes to this one here, just know one thing. Note, please. Note number one, please. Note number one, please. Want to note before proceed. Want to note, please. The relationship between angular acceleration relationship between angular acceleration and linear acceleration. And linear acceleration so relationship between angular acceleration and linear acceleration is given by the equation angular acceleration alpha is equal to linear acceleration, that's a, all over r. We know that we have acceleration in physics, that's a, and yet I'm seeing angular acceleration, that's what the alpha. The relationship is simply what the alpha equal to a over r. Your a there signifies your acceleration. So where a is simply the acceleration due to gravity, acceleration in what? In meter per second square. Your r there is the radius of curvature or radius of a radius of circular path, right? Radius of circular path. All right. So I have in meters, 1, 2, in meters. So it becomes the whole idea behind angular acceleration as shown in the board. So let's take past questions in the study of rotational dynamics and in the study of rotational dynamics, and we'll look at examples and past questions for the first, second, and third concept. Let's take past question in our next class, please.